So welcome to this short course on semiconductor fundamentals. By the end of this course, you should have an understanding that will allow you to understand the operation of almost any type of semiconductor device. In Unit 1, we're going to dive right in and begin to talk about some basic materials properties of semiconductors. And I'll be relying on some of the knowledge you have from an undergraduate chemistry or physics course, and we'll show how those concepts are extended and applied to real semiconducting materials. So let's begin with the simplest possible atom. This is probably where you started in freshman chemistry, the hydrogen atom. The hydrogen atom has a positively charged proton, a negatively charged electron. The two are held together by the Coulomb force, opposite charges that attract each other. And you'll recall that the electrons reside in states, and we label these states, or these orbitals, S, P, D, and F, you may recall. Now, another label for the states is the principal quantum number, n. n equals 1 is the lowest energy state, n equals 2 is a higher energy, and the energy just increases as the principal quantum number increases. Associated with each of these principal quantum numbers is a set of orbitals, the s, p, d, and f. And you may remember this formula. The energy is minus 13.6 electron volts divided by the principal quantum number squared. So this is some basic fundamentals that we learned about hydrogen atoms. Well, silicon is the most common semiconductor. It's much more complicated than a hydrogen atom. It has 14 electrons and 14 positive charges in the nucleus. So if we ask where those electrons reside, they reside in a set of states labeled by 1, 2, 3, and 4, the principal quantum numbers, and associated with each of those principal quantum numbers is a set of orbitals. So we need to fill up the 14 electrons into those states. We start at the lowest energy. We can put 2 electrons, one would spin up, one would spin down in the s orbital for n equals 1. We can put 2 more in the n equals 2 s orbital. You'll recall that the p orbital, there are 3 of them. Associated with the x, y, and z directions, each one of those can hold 2 electrons. So 6 electrons can be held in the p orbitals. So we can put 6 electrons in the 2p states. We can then continue to the n equals 3 states and put 2 electrons in the s orbital. And then we have 6 more states available in the n equals 3 level, but we only have 2 more electrons left. So we can put the 2 electrons in the 3p orbital, and we have 4 states that are empty there. Now you'll recall that in the early 20th century, the way people sorted out this understanding of atoms was by thinking of exciting an electron and putting it into one of the higher orbitals, letting it drop down and release energy. That energy comes off in the form of light. The frequency of the light is given by the energy difference is equal to Planck's constant h times the frequency. And understanding these discrete colors of the light that were emitted from the atoms is what led to the development of quantum mechanics and the understanding of these orbitals and energy levels. Now, this is a relatively complicated situation, and we're not going to be interested in most of it. The electrons that are in the lowest energy states, these are bound very tightly to the core. They don't interact with the outside world much at all, and they're not going to be relevant for us in this course. The electrons that we're interested in are in the highest energy state, the n equals 3 state. These are the electrons that are responsible for chemistry and the chemical bonds. We call these the valence states. There are 4 of them in silicon. But you'll recall that there are also 4 empty states in the 3p orbitals. So we have 4 valence electrons, but we have 8 valence states. Those are the ones that we're going to be focused on. So let's think about what we're trying to understand is not an isolated silicon atom, but a chunk of silicon crystal where there are a large number of atoms per cubic centimeter. So in a silicon crystal, there are about 5 times 10 to the 22nd atoms per cubic centimeter. And they're arranged in a crystal lattice. It has a little bit of a complicated structure. You can see it here. They're arranged in a cubic structure. There's a silicon atom at the corner of every cube. There's one at the face of each, at the 6 faces of those cubes. And then there are 4 more inside. If you look closely, you can see that each silicon atom is surrounded by 4 nearest neighbors. And that's important. The 8 valence states give rise to 8 times the number of atom states in the crystal. but only half of them are filled. But something very important happens. When the electrons are, or when the silicon atoms are put in a lattice a short distance away from each other, the chemical bonds form and the orbitals interact, and the discrete energy levels of the isolated silicon atoms change. In fact, we no longer have discrete energy levels. But before we talk about that, let me just give you a much simpler picture of that silicon lattice that we'll use frequently in this course. Rather than drawing the complicated three-dimensional structure, we'll draw this little cartoon. The important point about the silicon or other common semiconductor lattices is that each atom, represented by the black dots here, each atom is surrounded by four nearest neighbors. The lines here represent the valence electrons. There are four with each atom, and if we share those valence electrons between its four nearest neighbors, then we effectively have the 8 states that are available filled. That's the basis of a covalent chemical bond. That's what holds the silicon lattice together. So there's a very important concept that happens when we put atoms together and form bonds. When we have 5 times 10 to the 22nd atoms per cubic centimeter in silicon, we have 5 times 10 to the 22nd of these states. But the states change because of the interaction that occurs when the orbitals overlap and the bonding occurs. Instead of becoming discrete, they spread out and they change in energy. Half of the states lower in energy. This is what forms the energy, the bonds, and that holds the silicon lattice together. All of those states there are filled with electrons. Those are the valence electrons that are forming the covalent bonds and holding the semiconductor lattice together. Now, there were also an equal number of empty states. So those empty states get pushed up in energy, and they're available to hold electrons, but there are no electrons to hold. There's a gap between the states that are filled and the states that are empty. Inside of that gap, there are no states, so no electrons can exist in that state. That's a very important feature of semiconductors. It's called the forbidden gap. This is the situation at 0 degrees Kelvin. All of the valence band states are filled, all of the conduction band states are empty, and there are no states between them. So what has happened here is that in an isolated silicon atom, the states are localized. The electrons are localized, and they sit on specific silicon atoms. Once this interaction occurs in the silicon lattice between the orbitals that are very close to each other, the states become delocalized and they spread throughout the entire crystal, which means that electrons can move throughout the entire crystal. So that's a very important change that takes place from isolated atoms to atoms in a crystal. Now, what happens if we warm the silicon lattice up just a little bit, say to 300 K room temperature? Well, if we do that, there is enough thermal energy. You may recall that the thermal energy is proportional to Boltzmann's constant times temperature. So the silicon atoms are jiggling around in random thermal motion. They have an average energy of 3/2 kT. That jiggling around and that thermal energy can be enough that there is a small probability that some of those valence bonds are broken. So what happens is that when some of those valence bonds are broken, we no longer have the electron in the valence band. There are some empty states in the valence band, just a few. And where do those electrons go? Those electrons have gone to the conduction band. So we now have a few electrons in the conduction band. So this is the situation for a typical semiconductor crystal at room temperature. There's a large number of states in the valence band, and a tiny fraction of them are empty. There's a large number of empty states in the conduction band, and a tiny fraction of them are filled with electrons. Okay. Valence band has just a few states empty. Conduction band has just a few states full. And those two types of states, valence band and conduction band, are separated by this forbidden gap. The energy range is called the band gap E sub G. Now, since a broken bond produces a hole in the valence band and an electron in the conduction band, the number of holes in the valence band and the number of electrons in the conduction band is equal. This is a very important number. It's called the intrinsic carrier concentration. The electrons can move about in the crystal and conduct electrical currents, the holes can move around in the crystal and they can also conduct electrical currents. So the intrinsic carrier concentration, N sub I, is an important quantity. Now, as we do homework problems and work examples, there's a point that sometimes causes confusion in courses like this. So I just want to mention that. When I quote energy as being 3/2 kT and I quote it in electron volts, we need to remember that electron volt is not a legitimate unit for System International, SI, or MKS units. It's a convenient unit for us to express energies in, but it's not a proper unit for doing calculations. So when we do calculations, we'll have to work in a proper unit, an SI unit, and that's joules. So when I'm computing the average energy, I would take 3/2. I would multiply it by Boltzmann's constant, which is 1.38 times 10 to the minus 23rd joules per Kelvin. And then I would multiply by the temperature in Kelvin, 300, and the answer would come out in joules. So the average thermal energy would be 4.14 times 10 to the minus 21st joules. Well, that's not a convenient number to carry around in your head. So it's more convenient to think about these energies in terms of electron volts. You'll remember from probably physics or chemistry that the way we convert an energy in joules to electron volts is we take the energy in joules, we divide it by the charge on an electron, 1.6 times 10 to the minus 19th, and we get 0.039 electron volts. Now, if I'm going to use this energy in a formula and compute something, I need to convert back into joules and insert that into the formula. Electron volt is not a legitimate SI unit. So be careful about that when you're working homework problems. Okay, now there's another picture of what's happening when we break bonds and create carriers. This is the cartoon of the silicon lattice. Each atom is surrounded by 4 nearest neighbors. The lines are the covalent bonds that hold the silicon lattice together. If there's a little bit of thermal energy, there's a small probability that some of those bonds will be broken. Now we've got an empty state in the valence band. What happened to that electron? That electron is now free to wander around the crystal. That's an electron in the conduction band. So this is an equivalent picture to the one I showed earlier with the energy band picture. Okay. Now, so in semiconductors, we will talk about electrons and holes. When we talk about electrons, we're not talking about the electrons in the valence band that are forming the covalent bonds. We're really interested in the electrons that have been broken, that now reside in the conduction band, and that are free to wander around the crystal and conduct current. We also have holes in the valence band. Those holes are free to move. For example, an electron in this valence band could hop over and fill up this hole. Now the hole has moved over one. Then an electron in this valence band could hop over and fill up that hole. So the hole is free to move around. The hole is an absence of a negative charge, so it behaves like a positively charged particle. And we will think of both electrons and holes as being 2 types of charged carriers that carry the currents in semiconductor devices. Now there's also another process that can happen, and you can see there's nothing to prevent this electron from dropping down and filling up that hole and going back in the bond. That's called a recombination process, and those occur also. So we have this crystal lattice way of thinking about things. We have these energy band diagrams way about thinking about things. An energy band diagram is a plot of energy versus position. But when we draw these energy band diagrams, and we're going to draw them over and over and over again in this course, we're going to simplify them. Because what we'll find is that the empty states in the valence band are all very near the top of the valence band. The filled states in the conduction band are all very near the bottom of the conduction band. So there's no point in showing the top and the bottoms of these bands. So when we draw energy band diagrams, we will simply draw the top of the valence band, and we will draw the bottom of the conduction band, and they're separated by the band gap Eg. That's the way we'll draw energy band diagrams, and we'll see a lot of those in this course. Okay. Now, when we're talking about semiconductors, there are many parameters that we're going to be interested in that affect the performance of a device. There are 2 very important parameters that we can understand already. So if this is a pure piece of silicon, we'll call it intrinsic silicon, or it might be intrinsic germanium or other semiconductors. we've seen that that the thermal energy is sufficient to break a few bonds and give us a small number of holes in the valence band. The number turns out to be about 10 to the 10th per cubic centimeter. And we get an equal number of electrons in the conduction band, same number, about 10 to the 10th per cubic centimeter. So the two parameters that are extremely important for semiconductors is first, what is the band gap? Because that's sort of a measure of how difficult it is to break these bonds. For silicon, it's 1.1 electron volts. Other semiconductors have different band gaps. For example, gallium arsenide is another semiconductor. It has a band gap that's a little bit bigger. The thermal energy at room temperature, KT, is 0.026 electron volts. The probability of breaking one of these bonds goes exponentially with the band gap. The bigger the band gap, the harder it is, exponentially harder to break those bonds. So the number of electron-hole pairs at a given temperature is extremely sensitive to the band gap. In silicon works out very nice. It's an easy to remember number. At room temperature, the number of broken bonds, which means the number of electrons in the conduction band, the number of holes in the valence band, is almost exactly equal to 1 times 10 to the 10th per cubic centimeter. In gallium arsenide, the band gap is bigger, so it's harder to break those bonds, so the intrinsic carrier concentration is much less. Now, 10 to the 10th sounds like a large number, but we should be calibrated. Remember, there are 5 times 10 to the 22nd atoms per cubic centimeter in a silicon crystal. 10 to the 10th is a minuscule fraction of the covalent bonds that have been broken. Okay. Now, there'll be some concepts that we will talk more about as the course develops, but I just want to introduce the concept here, and then we'll return to it later in another lecture. You'll remember from your freshman physics that light can be thought of as a wave or as a particle. The particle is called a photon. There's an energy associated with each photon. The energy is given by Planck's constant h times the frequency of the light. If I shine light on a semiconductor that has a frequency that's high enough, or a wavelength that's short enough, so it's blue or violet or ultraviolet, then the photons will have a lot of energy. And I could, for example, take an electron deep in the valence band, and I could move it way up in the conduction band. But I said that the electrons and the holes are very near the top of the valence band or the bottom of the conduction band. So what happens? Well, what happens is very quickly, within femtoseconds, the electron will lose its energy and drop down to the bottom of the conduction band. Then it can't drop any further. What will happen in the valence band is that electrons in the valence band here will drop down and fill up the hole, so the hole will move up, and within a few femtoseconds, it will be near the top of the valence band. So we will assume in this course that the carriers are always near the bottom of the conduction band for electrons or near the top of the valence band for holes. And that'll be a good assumption. By the way, the reason we would call these hot carriers before they relax to the band edges is because we like to sort of think about energy and temperature. Temperature is a way of measuring the energy of a carrier. So when we're talking about effects like this, we talk about hot electrons or hot holes. Okay, we now have the background that we can understand what makes a metal, what makes an insulator, and what makes a semiconductor. You'll recall metals conduct electricity well. They usually conduct heat well also. Insulators don't conduct electricity well, and they usually don't conduct heat very well either. Semiconductors are somewhere in between. But the very important property they have is that their properties can be reproducibly controlled. Now, the way we would show an insulator on an energy band diagram is we'd show a material with a very large band gap. It's very difficult to break the bonds and create any carriers that can conduct current. For example, silicon dioxide, which is glass, has a band gap of about 9 electron volts. Remember, silicon was 1.1. The way we show metals is there's no band gap at all. We fill up some states, and right in the middle of a band, we stop, and the states above it are empty. So the electrons are free to move. If they need more energy, they just move up a little bit and find another state. There's no forbidden gap. What's a semiconductor? Well, it looks like an insulator. It just has a smaller band gap. It has a small enough band gap that at room temperature or at reasonable temperatures, a few of the bonds are broken, and there are a few electrons and a few holes that can carry current. Okay, we have covered a lot of ground. Let's wrap up. The important concepts are that if we take isolated silicon atoms, we have a set of discrete energy levels. When we create crystals of semiconductors, the covalent bonding holds the crystal together. The electrons interact with each other. The energy levels broaden and become bands of energies. Everything happens near the top of the lowest energy band, the valence band, and near the bottom of the highest energy band, the conduction band. That's the region of those are the two regions of energies that we're going to focus on in this course. The electrical current in a semiconductor or semiconductor device is carried by the electrons that are in the conduction band or by the holes, which we think of as positive charge carriers in the valence band. And the band gap and intrinsic carrier concentrations are the two most important parameters for a semiconductor. They're tightly related. The wider the band gap, the smaller the intrinsic carrier concentration, or the concentration of broken bonds. So we've covered a lot of ground. If it seems like a lot, don't be concerned. We will be revisiting these concepts over and over again as we go throughout the course, and you'll have a chance to develop some familiarity with them. So we'll begin next and continue the discussion in Lecture 2.